continue talking about limits at infinity and horizontal asymptotes. So here are the intuitive definitions we've been working with for limits at infinity. We're going to let our x's either grow or decrease without bound, and we're going to consider what happens to the function. So we say the limit of a function as x grows or decreases without bound is equal to L if it gets closer, the function gets closer and closer to L as x increases or decreases without bound. And if either of those limits exist, then we call y equals L our horizontal asymptote. So that value, that limit value of the function creates a horizontal asymptote if that happens at the ends of the graph. We've also now been computing these limits computationally rather than just looking at the graphs. We've been taking these limits and utilizing the fact that if we have a constant and we divide by x raised to some power, where that power is any rational number, then it turns out, and positive, any positive rational number, it turns out that that limit of 1 over x to the r is equal to 0, and in fact we can even have a constant. So this is where we're at. This is from the earlier portion of this section, and I want to just wanted to start off the video by just reviewing that and then jump right into several examples in this video. All right, so for our first example here on this video, it's actually our fourth example in the series of examples we've been working through. Let's take a look at this function. So 10 minus the cosine of x over the square root of x. And at first glance, we might think, well, why don't we just do direct substitution, because this would be 10 minus, let's just write this, even though this is kind of funky notation, let's write that in there and so that I can illustrate the problem. Here, of course, the 10 is, this constant is going to be this constant. It's going to stay the constant. So when we take the limit of a constant, that is equal to the constant. So we could actually take the limit of the 10 and that result would just be 10. Where we're a little bit hung up right now, though, is on this piece, because obviously the cosine of infinity is nonsense. Now, dividing by the square root of infinity, that is like an x to the r, and we could talk about that. But this piece right here is a bit of nonsense. Like I can't make sense of a cosine of infinity. And why not? Well, let's just make a note to ourselves and keep in mind that the end behavior of the sine and the cosine, so as the limit of infinity, the limit of the sine or the cosine of x as we approach infinity, infinity or negative infinity, the limit of the sine of x as x grows without bound, it doesn't exist. The sine of x is oscillating. It oscillates between -1 and 1. Okay? The sine curve, right, if we just think of what the sine curve looks like as we go out towards infinity, right, we've got this curve. Well, the same exact thing happens for the cosine, right? That limit, those two limits as we approach infinity, as we grow without bound, they don't exist because we have oscillation. I've drawn the sine curve here, but shift the cosine curve over and you're looking at the same graph. So we do not have limits at the infinity. They do not exist because of oscillation. The sine and the cosine will continue, they're periodic and they continue to just oscillate up, down, up, down. They are bounded, but they oscillate. And so the limits themselves, that's why I said this piece right here, this is nonsense. Like I can't take the cosine of infinity. That's nonsense. That's not mathematically possible. That limit doesn't exist. So I have to think of a better way to handle this. So what I'm going to do instead is I'm going to pull out a trusty little theorem from a couple sections back called the Squeeze Theorem, because of what I just said. We do know, now while these limits don't exist, we do know that these two functions, the sine and the cosine, are bounded, right? They are bounded functions, and we can utilize our squeeze theorem. So remember, the squeeze theorem says if we can squeeze a function between two other functions that have the same limit as we approach a value. And in this case, it won't be approaching a single value. We'll be approaching infinity or growing without bound, but we can still utilize it. So we're going to use the squeeze theorem, and we're going to remember that the cosine of x is a bounded function. It is always between -1 and 1. Therefore, we could divide that entire expression by the square root of x. Now, remember when we have an inequality, we can only divide an inequality by a positive quantity. So we would want to say since the square root of x is greater than 0. Okay? We do know that. And it has to be greater than 0. Remember, we're looking as x approaches infinity. It can't even be equal to 0. Well, I mean, it can't be equal to 0 because we would be dividing. I forgot to divide the middle term. There we go. Okay. Therefore, when we divide the entire inequality by the square root of x, what we do is we have now bounded, we have squeezed cosine of x over the square root of x in between two other functions. Okay. So what we can say now is this. We can say then the limit as x approaches infinity of -1 over the square root of x has to equal 0 because x is growing without bound. And the limit as x approaches infinity of 1 over the square root of x must also be equal to 0. And by squeeze theorem, I'm going to abbreviate ST, by the squeeze theorem, the limit of cosine of x over the square root of x as x approaches infinity must also be equal to 0. Okay? Now, we can't just say that up here where we had this nonsense, right? This piece was nonsense. We can't say that up there. We have to use some mathematics. We have to use a theorem that says that cosine squeezed, right? It is bounded in between two values. So we can take the limit of the cosine of x over the square root of x, but we have to do so by squeezing it in between two limits that we can compute using the rules that we have. So we have to squeeze it in between these two. All right, so that said, that was only dealing with this part. So now let's come back to our limit and let's finish this out. So the last line here is going to say that the limit because remember, we have to put that constant back in. So the limit of the function 10 minus the cosine of x over the square root of x as x approaches infinity is equal to 10 plus 0, which is equal to 10. So the limit, we did have that constant in there. We don't want to forget about that constant. Now the 0 came and had to be justified in the step above. Okay? So that came from the squeeze theorem. Okay, so something to remember with the sine and the cosine before we move on to the next example. Something to remember with the sine and the cosine. Sine and cosine are bounded. Now, their limits themselves as x is growing without bound, going to infinity, or going to negative infinity, decreasing without bound, their limits themselves do not exist, but they are bounded functions. And that is a fact that we can use to our advantage with theorems like the squeeze theorem. Okay? So always kind of keep that in your toolbox, right? Keep that as a tool. You know, you see the sine and the cosine, and if it's not a limit that you can compute directly, think about the fact that it's a bounded function, and does that help you at all? Okay, so let's consider another function. So let's take the function 5 minus e to the negative x over 3 plus e to the x. So much of limits sort of has to do with our confidence and our knowledge of all of the functions. So we just finished an example with trig functions, and it was really building off of our knowledge about sine and cosine and the fact that those are bounded functions. And here we're looking at a function that's built from exponential functions, and knowing what these exponential functions do and how they behave. So maybe a little thought bubble in my head, I see an e to the negative x and I see an e to the x, and I'm thinking to myself, exponential decay, right? E to the negative x is an exponential decay, and exponential growth for the e to the x. Now, one is in the numerator and one is in the denominator. All of that's going to have to be considered, but just the basics of the functions are going through my head, and I'm thinking, you've got your exponential growth function, e to the x, which looks something like that, and then you have your exponential decay function, e to the negative x. So you've got your exponential growth and you've got your exponential decay functions. So those are, just sort of running through my head, like that's how those things behave. We are talking about end behavior here. We're letting x approach infinity. So just at first glance, before I do any actual work, right, I want to have an intuitive sense as to what's going to happen to this particular function that we're examining that has these exponential growth and decay functions in them. I want to think about possibly what's happening here. And so as x is growing without bound, right, as x approaches infinity, if I think about what these graphs look like, I'm looking at this top, and in my head, I'm thinking, well, e to the negative x, as x approaches infinity, that exponential, that's a 0, right? That is going to approach 0. It's going to decrease, right? It's going to decrease down. It's a positive value. It's going to decrease down until it gets infinitely small. That's what happens as x approaches infinity on this exponential decay curve. Well, what's happening as x approaches infinity on an exponential growth curve, right? So in the denominator here, what's happening? Well, in the denominator, I've got 3 plus. Notice as x is approaching infinity on my growth curve, the exponential growth curve is going to grow without bounds. So it's like I got a plus infinity right here. And so in the denominator, I've got a 3 plus infinity is what's going to happen. So in my head, I'm kind of thinking about all of that, and I'm thinking, well, what would that do? How does that look? How can I show that mathematically? And essentially what I have here is something in the numerator that is who cares about the 5? Who cares about the 3 in the bottom? Because in the top, 5 plus 0 would just be 5. And in the bottom, that's going to be infinity. And 5 divided by something that grows without bound is 0. So how do I show that mathematically? How do I make that really nice and clear here without the graphs and all my highlighting and all of that, right? Just wanted to explain that this is, as I'm thinking about this is my thought bubble as to what must be happening here, right? As I'm thinking about this function and what these exponential growth and decay curves mean to me. So how am I going to do that? Well, I'm going to take an approach similar to how I did with the rational functions. I've got a fraction here, and I'm going to think about what would be the lead term. What's the term in the denominator that is dominating the denominator? And obviously the 3 is just a constant, stays fixed, while as x approaches infinity, that exponential growth, again, these are the things that went on in my mind, it happened in my mind as I was setting this up. This denominator gets just obliterated essentially by the e to the x as x grows without infinity. So I'm going to take an approach where I'm going to take that same technique discussed in the previous video. I'm going to take that same technique, and the technique that we're using here is to divide all terms by, and we were talking rational functions, so I'll put it in parentheses here, but by the highest powered or degreed term in the denominator from denominator. Now, this is obviously not a powered term, so that's why I have this in quotes here. Obviously, we're not talking about a rational expression, but I'm still using that same sort of technique. The denominator is being dominated by that e to the x, that exponential curve. Exponential curves, as we approach infinity, just have explosive growth, okay? And since it's being dominated by that, I'm going to use that to simplify and be able to show my work on this limit, because now I end up with a 5 over e to the x. This becomes 1 over e to the 2x, just using my rules of exponents, subtracting exponents and then dropping the negative exponent to the denominator. Then I have 3 over e to the x plus 1. Okay? And so what's going to happen here? Well, what's going to happen here is this entire numerator, each of these little terms now, we can utilize the fact that as x grows without bound, e to the x is also growing without bound. 5 divided by infinity, that's going to approach 0. 1 divided by infinity is going to approach 0. 3 divided by, and I'm saying divided by infinity because it's easier than repeatedly saying 3 or 1 or 5 divided by something that grows without bound. So I'm saying divided by infinity, and that is just mathematically a way to say we're dividing by something that is growing without bound, just getting infinitely large. And then, of course, the constant stays the constant. And so what I end up with here is 0 divided by 1. And 0 divided by 1 is definitively 0. And that is my answer. Now, look at back up to my little thought bubble on the top. And my thought bubble on the top gave us something very similar there too. Okay? And so we are intuitively thinking in the right way when we think graphically about what happens to the exponential decay and exponential growth functions. But here we've been able to mathematically show that using a constant divided by something that's growing without bound. All right, so let's continue with another example. So here we're taking the limit of this function that has a root in it and minus 3x. So the square root of 9x squared plus x minus 3x. And we're going to, I let x grow without bound, but we could easily have just switched that up. And maybe at the end we'll come back and talk about what might be different if we were going that direction. So as x approaches negative infinity instead of as x approaches positive infinity. So how are we going to do this, right? Like always, like our first thing is to come across a limit, and I'm hoping you guys are building up some skills where you can take a limit and you can kind of think like intuitively what's going to happen. Like if I just I can't just mathematically like throw an infinity in here without some thought process to that and maybe some manipulation, but what would happen if I did, right? Like let's just thought bubble this for a second, okay? What's going to happen? So if I do that, if I throw in an infinity, right? I square infinity, I multiply by 9, and I add another infinity, right? I know it sounds funny to say that, but that's what we're doing in our thought bubble. And I get like the square root of infinity. Well, the square root of something that's growing without bound is going to also grow without bound. So essentially I get infinity out of the root, and then I'm subtracting 3 times something that's growing without bound. Well, that would be also an infinity, okay? And this is something that we can't compute. We can't like really think about what this might be. This is like a power struggle. Like who is going to win? Is the root function going to win? Is that going to grow faster than the 3x term because we're subtracting? So does the first term in this expression dominate and win, essentially creating an infinite behavior, or does the second term win this infinite battle that we're having here? And does that second term, as we're subtracting infinity, does that dominate and give us something that decreases without bound, goes to negative infinity? Or is it something totally different where like these two maybe approach at the same rate and you've got something like 0, right? Like this is just a big fat question mark. We don't know. This is what we call an indeterminate form. We're not really sure what's going to happen here. We can't even really intuitively get a sense of what's going to happen here. We have to just get in there and try to manipulate this expression so I don't have something that is indeterminate, something I cannot determine what happens with. I have to have something that I can actually determine. So what are we going to do? Well, anytime I see a root, my thought goes to, why not try a conjugate? Why not try playing around with some conjugates and see what happens? So I'm going to take this, right? That's kind of my like, well, I see roots, let's go conjugate, right? Might as well give it some fireworks. So let's take the limit of this expression. So let's take our 9x squared plus x minus 3x, and let's multiply by the conjugate. So let's multiply by 9x squared plus x plus 3x. I know that that will make my expression, when I multiply it by the conjugate, I know that that will make that expression simplified in the sense that it will no longer have roots. And I like that, but I can't just multiply it by its conjugate. I have to also divide by its conjugate because I can't change the function. I can only manipulate it algebraically. So I do that, and again, I have not taken a limit, so I need to continue to carry my limit notation down. When I expand this, when I multiply these out. The two middle terms will cancel, and to save time and space, I'm not going to write those in. I'm simply going to write the product of the first two, which is the square root of 9x squared plus x times the square root of 9x squared plus x. The square roots drop, and I have just 9x squared plus x. And then the two middle terms cancel, so then the product of the last two terms is a minus 9x squared. And in the bottom, this was over 1. So in the bottom, I just have that conjugate, 9x squared plus x plus 3x. Now notice in the top that the 9x squared terms cancel, and I have the limit as x grows without bound of simply x over, and now in the bottom, I have 9x squared plus x plus 3. Okay. All right. Shoot, I haven't gotten too much further, right? Like, because I'm looking at this now and I'm thinking, okay, well, I had that big fat question mark up at the top with my thought bubble, and right now I have a similar big fat question mark because I'm going to have something in the numerator that approaches infinity, and I'm going to have something in the denominator that approaches infinity. And once again, this is not something I know what happens. Like, who's going to win? Is it going to be the numerator? Is the numerator going to dominate? Is the denominator going to dominate? Is it some sort of balance between the two? So I'm still sort of stuck. So I go back to that technique that we've talked about, that technique where we're going to divide by high, I'm going to shorten it, high power in denominator. Okay, high power, and I'm going to, I say high power, we used it with exponentials too, rather than just high power, high term, maybe we could say. But I'm going to look at the bottom and I'm going to say, what is the highest power in the denominator? Now, I see this x squared, my eye might go to that and think, oh, the highest power in the denominator is an x squared. But remember that that is actually under a square root. So when you take x squared and you take the square root of it, you actually just get x. So the highest power here in the denominator is actually just x. So I'm going to write this, so I have some space, and I'm going to use the highest power in the denominator is going to be x, and I'll put that in quotes right there. So I'm going to take x and the square root of 9x squared plus x plus 3x, and I'm going to divide everything by x. Now, when I do that, we'll have to be a little bit careful, but I'm going to divide every term by x. Okay. Another way to think of that is I basically multiplied the top and the bottom by 1 over x, and then I distributed. Okay. All right, moving on. So this is actually, let's take a look. This is 1 in the numerator and 3. Now, what do I do with this piece, right? Because I want to simplify that, but I can't bring that x under the square root unless I make it also under a square root. So how do I deal with that little piece right there? And we have this nice little we just have this nice little fact that says this. It says that x is equal to the square root of x squared if x is greater than or equal to 0. Now, that's the fact that we're going to use. Remember at the beginning I said we could actually consider what happens if we were going to negative infinity as well. If we were going to negative infinity and our x's were negative, we would have to use the second half of this fact. And this is a fact worth let's make it in like a rainbow sparkly. This is a fact worth remembering as we work with algebraic manipulations. Anytime you want to bring something, a variable under a square root, you can use this fact. You can use the fact that if, I'm going to actually change it to black. You can use the fact that if our x's are positive, x is equal to the square root of x squared. And that has to do with the fact that when you square something and take the square root, you have an absolute value. So if the quantity under the square root is greater than 0, then you can say x is equal to the square root of x squared. But if the quantity you're talking about is negative, you have to force that negative by putting that negative outside of the square root. It has to do with the way we define square roots. So this is a very useful fact. So what we're going to do here is we're actually going to come in and we're going to say 9x squared plus x over the square root of x squared. We're using this fact right here, okay? So we're using that fact and we can say that that's okay, right? We can justify that since x is approaching infinity, the square root of x squared is equal to x because x is greater than or equal to 0. Okay? So we can use that. We can absolutely say that that is the case. Okay? Okay, so that is a super useful fact. I'm going to put that there. It's in this section and in this example, but it's a useful fact certainly beyond this example in this section. Okay, so let's keep going here and let's grab this and finish it out. So the limit as we're approaching infinity is 1 over, I'm going to simplify that square root. That becomes 9 because I can bring the x squared in now. 9 plus 1 over x squared plus 3. And now we can actually take this limit and not end up with anything funky or unknown, because as I take this limit, the numerator approaches 1, the denominator approaches 9, because this piece, this 1 over x squared, as x grows without bound, goes to infinity, becomes 0, and plus 3. And of course, that's 1 over 3 plus 3, so that answer is 1/6. Now, because I'm running out of time and I don't have time to do a whole nother example where this is negative infinity, I want to just extend this and I want to say what would be different here. So how would this be different if I were taking, so let's just consider for a second, if all I did was take this same limit, same function, and I took 9x squared plus x minus 3x as x approached negative infinity. Okay? Our process would be exactly the same, ... same process. So I won't go through that same process again, that same thought process. We'd get that infinity minus infinity. Actually, we would have an infinity. This one would become infinity. Well, we would have some issues inside the square root. So we'd have to worry about that and consider that for a second. But the part that would be different would be right here where we are considering what happens as we divide by this x squared. So this fact with my little sparklies there, we would have to do a little adjustment right there. And it would actually, now that I'm looking at it, it would give us a negative. We would end up with a negative. We could come back through here and we would have a ... We would end up with the limit after we did all of the conjugate and all of the simplification. That's the part I'm going to skip, and I'm going to end up right here where I have that 1, and I'm even going to do the whole, I would divide by it. I do the whole thing that we have right there, and I would end up with a 9x squared plus x over the square root of x squared, but I would have to put a negative on it, plus 3, since as x approaches negative infinity, the square root of x squared, the negative square root of x squared, is equal to x when x is less than 0. So I would have to be careful of that piece right there. As we're approaching negative infinity, the square root of x squared has to have a negative in front of it if our x's are less than 0. So this would have to have a negative in front of it. Then we could continue this down. Sorry, my limit gets all squiggly when I'm zoomed out like that. So this would be the limit as x is approaching negative infinity. We would end up with 1 over, and now in this case we would have a negative outside the root. We would have 9 plus 1 over x plus 3. This would give me a 1 over, I would have a negative 3 plus 3, which is a 1 over 0. And I would have to think about what happens is this, how is this directional? Because this is infinite. So this is definitely infinite as we're heading out towards negative infinity, but which of those infinities is it? Does it approach positive infinity or does it approach negative infinity? So we have to think about what side of 3 this is coming from right here. And so if we take 9 and we add something here that is approaching 0, we have to think for a second about which side of 0 it's coming to. And since it's negative infinity, this is going to be approaching 0 in a negative way. We're approaching 0, so we're having slightly less than, we're approaching 0, but we're slightly less than 0, meaning we're just slightly negative. So that means that this is negative 3 from the left, and this would be then 0 from the left, and we are actually getting a negative infinity. So I wanted to add that in there because we would have the same process, but we have this fairly major difference where we have to remember that negative when we replace x with the square root of x squared. And that is important. You have to consider when you're working with a variable, you have to consider the sign of the variable when you make some adjustments like that, when you take the square root of an x squared. So this would be approaching, this particular limit on the other side, as x approaches negative infinity, would actually be decreasing without bound, going to negative infinity. So lots of subtleties within this problem, and we have to be careful that we get through a problem like this and that we're careful with our signs and show all of our steps.